So today we're going to finish up friendship. It's not too bad. And then we're also going to start talking about templates. So when we left off yesterday, we talked about how to we talked about how to declare a friend, declare a class or a function your friend. Right inside your class, you say friend, name of the class. Or if you want to say some other function is your friend, signature of that function. And remember, these calls here are making B a friend of A. This makes Max a friend of A, right? We're saying who's our friend. But friendship isn't mutual. Just because you declare someone to be your friend doesn't make them if you say that they're your friend, doesn't make them say that you're your friend as well. So if I say B is A's friend, right? A is not B's friend. So B has access to all of A's private members, but A has no special access to B. So be careful with that. The other thing is that friendship is not transitive. If I like the friend of my friend is not my friend, right? So if I say that A's friend is B, and I say that B's friend is C, C is not A's friend, right? It's not transitive at all. So C has no special access on A. Again, we'll eventually talk about inheritance probably next week. But if you have a child class, like friendship is not inherited. So, if your parents have friends, your parents' friends aren't your friends. You have to explicitly say that the child is also the friend. So if I have a class A and I say that B is my friend, right? Then I have a class little a, right? And a class little b. This one, little a is a child of big A, and little b is a child of big B. Little b has no special access to A, and little b has no special access to little a. Big B has no special access to little a. Big B only has special access to A. So only who you directly say is your friend. That's it, period. Any questions about friendship? Yeah. No, because friendship is not mutual. Right? If B didn't say that A was his friend, so A has no special access to B. I did. Yeah. You should have access then, because your type is particularly of A's type, no longer little a. So then let's talk about templating. So sometimes when you're writing code, you've probably found the problem where you want to do the exact same thing to two different variables, but the only reason that you can't make them pass to one function is because the types are different. For example, you might want to be able to find the max of two integers and also want to be able to find the max of two strings, right? The code here is identical except for the types, right? There's no difference there except one accepts strings and one accepts integers. Which would really suck if we had to keep, rewriting our code over and over and over again for every different possible combination of two things that we ever want to take the max of. So this is where we use templates. The way that you declare a templated function is template, and then you can either say type name or class, and then you list the names, then you list so type name, and then basically you're templated over how many different types. So this would be, if you said type name T1, I'm templated over a single type. Type name T2, I'm templated over T1 and T2. Inside the function, T1 and T2 are just going to be the names of types. But we just don't know right now what they're going to be. And we'll see later on how we can figure out what they will be. You can say class here instead of type name, but I like type name because it's a little bit more specific that this is the name of a type. T1 is the name of a type. If you name your type over here just T, the compiler is able to automatically deduce when you have an instance of that class what the type should be, and you won't have to specify when you write it what it should be the type of that object. So over here, if we wanted to template max, right? Max now accepts, it's templated over T, and so we accept two T's and we return a T. And then again, the code is exactly the same. Return A greater than B, question mark. If A is greater than B, return A. Otherwise, return B. But now I don't have to keep writing this for different types. If I want to make an instance of that particular function, right, with some particular set of types, I have to instantiate it, right? And you've seen this before when we've been working with vectors, right? I want a vector of int. I want a vector of string. I want a vector of int, right? The triangular brackets were where you were specifying the particular type of vector that you wanted. So over here, right, I want a max function that can take the max of integers. So max of these integers, 3 and 4. I want the max function that can find the max of strings. Max string is the types that I'm templating over. So here, hello and help, right, we get the max of some doubles as in terms of the types that we're implementing. And so what the compiler really does, it's going to rewrite 3 separate max functions. One for integers, one for strings, one's for doubles, and then we'll reuse the one for integers down here. Any questions so far? Yeah. I mean, like, how can I figure out whether it's really going to work or not? Right, so here we're making some assumptions about the types that are passed in. We're assuming that the greater than operator is defined. If the greater than operator is not defined on those types, then you'll get a compile time error that says I can't do this because I can't find a greater than function to call. Yeah, there is, but that's like a really advanced topic with like type traits. So you can like look at the traits of your type, and if the type has specified these traits, and you can do conditional logic on there if you want to instantiate or not, or if you want to instantiate different versions of a template. So right now, what we were doing before when we were doing max, right, we assumed that the two types had to be the same, right? I want a template of type T, right? Both A and B had to be the same. But what happens if we want to be able to compare like integers and doubles, right? Or integers and strings for whatever reason, right? Or two things of two different types that happen to be comparable. The version that we wrote won't work. So now what we could do is when we declare, our template, we have just two types, right? T1 and T2, and we're making some assumptions over here that when you compare A and B, right, that the T2 can be cast to a T1, that it's convertible. If it's not, we're going to have issues and the code again wouldn't compile. This would allow us to compare two different types together. You can also specify default parameters for your templated types. Just set it equal to what you want the default type to be. So here we said that T2 defaults to T1 if it's not given, right? T2, like the default parameter could be some hard-coded type like bool or int or double or my class, whatever it happens to be. It doesn't have to be the other template parameter. It could be any type that works. So let's say you want to template a class. That does happen from time to time. In general, it's very common that you want to template classes when you're looking to build a container, right? I need to hold some objects. So you have like the vector is a templated class because I want to have vectors of holding different types of things. Or the math is also templated because I want to be able to hold different types of things. Or I might have a tree, also would be templated over the type. For your next homework assignment, you're going to have to do a doubly linked list, but you're going to have to be able to implement a doubly linked list of any type. So we template over the class. So over here, I made a class called myPair. It's templated over types 1 and types 2, and type 1 defaults to type 2. And I have a constructor that accepts a T1 and a T2 reference, and I have two member variables, first and second. Right? So this will just be a way of collecting two things together. Any questions here on templating class? Yeah. So if you have multiple template parameters, can't figure it out, I think normally it only works with one where it's able to do the deduction. And you can always try with two and see what happens, but you'll probably get some compiler error that this does not name a type, or you need to instantiate it or something. Anything else? So if you want to define the template outside of the class, or define that function outside the class, again, you have to specify the template parameters again. And then when you're listing the type of your variable, right, like what my pair am I, you have to specify again the template parameters in here. Because a my pair doesn't name a type, right? It has to be a my pair of integer and string, or my pair of character and character, or my pair of double and float, or my pair of string and vector of integers, right? Just a my pair doesn't name a type. It has to be a particular instance of a my pair. So here I have a my pair of these two types, T1 and T2. If you do a default parameter, you don't specify it again here, right? And then I have, again, my pair. It takes as its first argument a T1. Second argument is a T2. The first gets initialized to first, and second gets initialized to second. We'll skip inheriting, but you can inherit from templates, and we'll wrap back around to that. But really what the templating is doing is it's plugging in those types when you list in the instantiation into like the T's to figure out what code it should write. And it literally just like writes the code that should be there and then attempts to compile it afterwards. So again, we have our little max function over here of T1 and T2, and we want to return who's bigger. So if I say like the max of an int and a double, what the compiler is going to create is this function over here, a max function that returns an integer, accepts an integer as the first parameter, and a double as the second parameter. If I say the max of string string, it's going to create a max function that returns a string and takes two strings as arguments. So it's literally basically writing the code that would need to be done for that particular type. It just substitutes the type in. Any questions? Yeah. So it's defined based on their greater than operator. So when the two strings are compared, the default greater than operator for strings does like a ASCII comparison between the values. So it works like store comp. But you could always define it to be something different if you wanted to. And there are ways of doing what's called template specialization, where you say, hey, this is a function, and if you put two strings in here and you wanted to instead return their length, you can have it so it just returns whoever has a larger length. But you'd have to specialize the template to do that, and we may not have time to talk about that. One of the things about templated code is that it shouldn't be compiled, right? It tells you how to write other code. So you're never going to compile templates, and in general, all templated code goes in the header file. You need to include this header file basically anywhere you want to use the stuff that's included inside of it, because the compiler needs all that information to know how to instantiate the things. What code should I be writing? Don't compile it. You can split your program into a .h and a .cpp like you've seen before. But again, you wouldn't ever compile that .cpp file, because again, it just contains header code. It would just allow you to do that split so things look nice. What you would do is at the end of the .h, you would include the .cpp. Make it one gigantic long file, and the .cpp would include the .h, and the guards protect it from like circularly including itself over and over and over again. If you do decide to split it up like this, you're going to have to mark those files that are .cpp as header only, so that the CMake doesn't try to compile them, because by default it's going to try to compile anything that ends with .cpp or .c. So things we didn't cover about templates, because it's a really broad subject, are template specializations, which we can show you that. That's pretty quick and pretty easy. How to partially conceptualize partial template specialization, parameter packs, functions of any number of arguments or of any type, the ellipsis operator, and template metaprogramming. These are all really advanced topics, which we won't touch in this class. But if you're curious more about templates, Google these terms and you get more information. So right now we're going to do some examples. Unless you guys have any questions before we move on. Whenever you instantiate an instance of the template, you do have to provide the types. There are some times where if you only have like a single type parameter, you wouldn't have to, and the compiler can deduce the type for you. But like once you create your vector event, right, you don't keep saying vector event, vector event, vector event everywhere, right? Or you don't say like, you know, my vector v1 of int dot pushback, right? It just needs it to know how to create the variable at that point. So again, I don't know why these have short name on them. That's fun. Ignore them for a second. But you can see here we've defined our functions. They're called maximum short name and minimum short name. They're templated over just one type T. And again, my cursor is dying because of C line. The minimum probably should be like A less than B. And then over here in main, notice it's all in the header file. So we've defined some operator less thans for a vector. And for unsigned long I equals 0, I less than unsigned long v1 dot size. What happened here with this file? Oh, okay, here we go. Oh, I was down there for a second. That's why things were making sense. Oh, this is all confusing. Let's just write some stuff over here instead. So again, if we wanted to write max, oh my goodness, template, type name, D. That would give us a max. We'll call it my max so the compilers don't get confused. And we could also repeat again for my min. We just flip it to less than. One other common thing that we like to do is like swapping two values. We want to exchange their values. So template, type name, T. Let's say we wanted to write a swap function. What do you think the swap function should return? Void, right? So we have void my swap. What should its arguments be so that we can swap them? We don't have to do pointers, we could do references, right? So we could have like T reference A, T reference B. Okay, what should we do in here? Yeah, we have a T temp who's equal to, yeah, sure, A, right? Then A equals B, B equals temp. Great, and now you never have to write a swap for a particular type ever again. Pretty nice, right? What about if we wanted to say, well, one thing is like, you know vectors, right? You can't see out a vector. They don't have an overloaded outstream operator defined on them. It's not defined. So what we could do is we could write an overloaded outstream operator for a vector of any type, right? Because what do you think like an overloaded outstream operator would do for a vector? What do you think it should do? Just output everything that's there, right? So we could just do template, type name, T. This is still going to need to include now std or iostream. And we would have as our output an std : outstream ostream reference operator out, and it takes in an std : ostream reference out, and we take in a const vector, std : vector of what type? T reference, call it vec. And now what should we do? Yeah. Because that's what the outstream operators do. That's what lets you do like cout, like variable 1, arrow variable 2, arrow variable 3. Like what it does is it evaluates the first one and like prints out like the number 3, and then it gives you back the stream as the return value. So now you have the stream, then you go and you do the second variable like 4. So what should we do here? For right. You like const auto reference val in vec. Right. We could use the iterative for loop, right, for each for loop, and then we could just do out arrow val, and then maybe followed up by a space, and then we can return out. And great, we now have overloaded the outstream operator for all vectors. Does anybody have any questions here? Yeah. So the question is, what happens if it's a vector of user-defined types and that user hasn't defined an overloaded outstream operator? Then the code wouldn't compile, right? But one thing with templates is unless like this outstream operator is needed, it would not be actually generated. So let's say you had a vector of user-defined types and you never tried to like see out that vector of user-defined types, this code would never be generated. So it wouldn't cause any compile errors. It would only be as soon as you tried to see it out that this code would need to be generated, that then it would fail. So this isn't adding a method to anybody. It's creating a new function called operator out, or operator left shift, that takes in 2 parameters, an outstream and a vector of type T. So this is not a member method of outstream, nor is it a member method of vector, right? It couldn't be a member of vector because vector would need to be on the left-hand side, so it couldn't be there. And we're not actually adding any member to the outstream operator either, even though it kind of might look like it. It's just a whole standalone function, right? Because like this function here doesn't have a this pointer, right? There's no this that I can go to. I also have no special access to any of the private member or protected member variables of the outstream. Any other questions? Yeah. So you only need to write template type name, and this name over here can be whatever you want if the function's templated, right? Right? You could call this guy over here like val type, and that's fine, right? The type name of this is the value type, right? Whatever the value happens to be. I mean, like but again, like just like we use I for loops, right? T is the common name to use for a type if there's only a single parameter. Yeah. So the left shift operator is only going to be defined differently here for outstreams and vectors. So you don't link against headers, right? You have to, like, because it's all a header file route, you have to include it, and it's not compiled, right? It generates the code that needs to be a part of that object there, right? So you can't link against the header file. The other thing is, so if you're like asking, like, is it going to change how like an int shifted to the left by another int is going to affect? No, because that's not an int and that's not an int. So it's not going to change anybody's behavior unless they also had defined like an overloaded left stream operator, overloaded left shift for an outstream and a vector, right? But then the complaint would be there's two definitions of that same function and it wouldn't compile. Any other questions here? Yeah. No, you could define an outstream operator for, I don't think you could define an outstream operator for the built-in types because there's already one there. But, you know, you could define an outstream operator for any other user-defined types you've created. Anything else? Okay, so let's go over here to main. Oops. Hmm? Okay, there we go. And then, right, we have our vector up here of integers and our vector of doubles. So now we can say, you know, std : cout v1 is equal to v1. v2 is equal to v2. Right? We can also do something like swap AB. And we want my swap. We go and build. Made mistakes. Okay, it built. One of like the worst parts about working with templates, which you're not seeing right now, they didn't make mistakes, is they produce some nasty compiler messages. for you. Like, it's pretty nasty. It'll be very, very obtuse as to what's going wrong. So, you know, I printed out, you know, our vector, printed out our other vector, no issues. If you wanted to print commas in between them, you could put commas in between them, right? We can just pop back here and say, oh, well, I want, instead of just spaces, I want comma space. But, you know, sometimes it looks a little bit ugly because it throws in a comma at the end. Oh, string, 2 characters, yeah. But, you know, sometimes this looks a little bit nasty where you have to say, like, you know, for each one but the last, print out a comma in between it. Because now we'll have commas at the end. It's now there. But it's nice not having to retype that code for the different types. The other thing that I want to show you guys, unless you have questions here for functions, templating functions. Yeah. So, like, this is like a for each, right? What you'd have to do is, then you'd have to assume, again, you're kind of assuming here that an iterator is defined over that type. So you'd say, like, for, you know, const iterator equals, you know, dot c begin or whatever, not equal to c end, you know, -1. Because for vectors that's supported, because they're random access iterators, so you can do like -1. So it'd be like the one before the end, right? Then you would stop, and then you would also then have to print out the one before the end right afterwards. So just like you would do it for anything else. So you guys remember how we talked about unique pointer? Right? Well, ever curious about how that's written? At least, you know, in implementation? So here's my class. It's called unique pointer, but, you know, it's all in caps instead of unique underscore pointer. And it's templated over type T. So we have a T pointer reference to the original. This guy right here is a right-hand side reference. Don't worry about that. That's just what you use for when you're moving things around. Basically, a right-hand side reference is something that can only appear on the right-hand side of an expression, right? If it can't appear on the left-hand side, it's not a left-hand, it's a right-hand side expression only. So over here, I delete my copy constructor because I don't want to copy unique pointers. And I also have a move constructor over here, so I'm able to move values from the right-hand side, and I also have a destructor. We've also defined an overloaded operator for operator move equals, but we've deleted our copy equals, right? Because again, you can't copy unique pointers. Then we have our dereference operator, which returns a T reference. We have our dereference operator, which returns a const reference. And then we also have our arrow operators, which return T references. And then an operator bool, are we valid? Operator equal, are 2 unique pointers equal to each other? Which, you know, that probably shouldn't ever happen, right? Because you couldn't have 2 unique pointers pointing to the same thing. And then not equals. We also have get, release, and reset. And we also have a swap. We're able to swap with somebody else. And we have as our member this T pointer, right? A pointer to some type. Don't worry about make unique right now, but, you know, he's cool and he uses argument packs and ellipsis operators. So this version over here, I did it where I split it apart across 2 files. So notice that I include unique pointer.cpp at the end, right? And count include just means, right? So I'm just copying and pasting this code into there. And I also include unique pointer.h here. The other thing is in the cmakelist.txt, I set my template properties for these guys to be header file only. There's also like a target source file, which you'd also use to do it as a target. But I made it, hey, I don't want to compile that function, the .cpp. My template files were unique pointer.cpp and unique pointer.h. These guys are only headers. So Here's our functions. Again, notice that since I'm doing an out-of-class declaration, I have to say, well, this unique pointer constructor that takes no arguments, well, what instance of what unique pointer is? Well, it's a unique pointer of type T, some arbitrary type. And again, if we get no arguments, we should be initialized to null pointer. If we get a single pointer, I should be initialized to that. And we also decided when we did this last time that we were going to make the person that we got that gave us the pointer, we're going to turn it to null so they don't use it anymore. This is probably not actually how unique pointer works, but you could do it if you wanted to, right? To make sure that you didn't accidentally dereference or like use it later on, because you should be using it through the unique pointer at this point. But again, this is like a design choice. And then here is the right-hand side copy. So I make I make my pointer equal to whatever the right-hand side is. And then I set the right-hand side equal to null. I need to take the value from them and steal it. So one of the things that kind of was introduced in C++ 11 and was a bit more supported in 14 is the idea of a right-hand side reference and moving. So if you think about moving is a bit different from copying in that when you move something, a lot of times you steal it. So for example, if you had to make a copy, or if you wanted to copy a vector, right? You have to copy all the individual elements that are inside of it, right? But if I wanted to move a vector from v2 into v1, I would only have to copy the pointer to that space, which is a lot faster. So moves are destructive in that they destroy the original object that they pull from. So here, since I can move from one unique pointer to myself, I need to steal his item. I also call the copy constructor over here, or not the copy constructor, but this instance over here. So this causes me to reset, and I make my pointer equal to the right-hand side, and the right-hand side pointer equals the null pointer. Any questions so far? Yeah. The double ampersand over here is a right-hand side reference. So basically, a right-hand side reference is something that can appear only on the right-hand side of an equality statement, like an assignment, right? So for example, when you do like, variable v1 equals like some function return result, or equals 3 plus 4, those things can't appear on the left-hand side. And so the right-hand side reference is kind of for things that cannot appear on the left-hand side. And this is how we denote moving. It also has another context in terms of templates called a universal reference. But again, you have to read a lot more about templates to get that stuff. Mostly. A little bit different, but mostly. So over here we have our destructor. So if we're pointing to something, delete it. So here's our move operator, right, where we're trying to assign unique pointer 1 is equal to unique pointer 2, but we're trying to move the contents of unique pointer 1 into ourselves. We first have to reset and get rid of whatever we were pointing to. Go ahead and destroy that, right? Then make my pointer equal to the right-hand side, make the right-hand side's pointer equal to null, and then we return ourselves. Right, we need to steal it from the right-hand side. Our operator star just dereferences our member, and our const 1 does the exact same thing. Dereferences the member. The arrow also just dereferences the member too. So operator bool, are we valid? We'll return, are we not equal to a null pointer? Operator equals equals. We check to see if our pointers are the same, but again, this situation should never happen if things are going good. Operator not equals. We check to see if the pointers are not equal to each other. If we want to get, right, we need to be able to return our pointer that we're holding. So we return a t pointer, t star, return pointer. When we release, right, we give up ownership over our pointer and give it back. So we have a t pointer temp equals the pointer. We are now equal to null. We own nothing. And then we return temp. Reset is if we have a pointer, delete it, and then we equal to null. And then we might also reset to be a particular pointer. So we call the first reset with no arguments to delete our stuff. make our pointer equal to the new pointer over here. And then again, this was a design decision. We chose to make the pointer that we passed a null so that we didn't make mistakes with it later on, right? Didn't try to reuse it in other places. Swap, right? We're able to swap what we're pointing to. So pretty similar to what we wrote before. So we move the value over into a temp because again, we're not copyable. Star this equals std move other. So then we grab what's in the other, and then other gets equal to move the temp. So we swap those two values. And again, we have to use move here on the inside to turn this basically what's a left-hand side reference into a right-hand side reference. That's what move does. You give it a left-hand side thing and it makes it a right-hand side. We just swap the values, and it's pretty similar to the swap that we wrote before. And this is more or less how unique pointer is implemented. You guys have any questions about like doing the typing here for the class? Any questions on templating? Do you have questions as to when you might use templates? Okay, and if you wanted to see what make unique looks like, this is always kind of fun. What we do is we say, hey, I want to make unique, so I need a unique pointer of type T, and I need to create a new instance of T, right? So we're making a new T, and then we keep the types of whatever happens to be there on our arguments, and we forward that to our new T. So we give T all of the arguments that we were given. Right, go call that instance of that constructor, or go call new on that to make the space, and then we get assigned that value. We give it back. I guess we should get into our next topic. And then tomorrow, well, I guess we'll start that today. Probably good. So how many of you guys have played Pokemon before? How many of you guys have ever played any turn-based game where two people beat each other until one of them dies? Right? That's kind of like Pokemon, right? They keep fighting until one of them dies, becomes unconscious. All right, if you think about like Final Fantasy is like just having like multiple Pokemon at once on the screen. They're all fighting each other like in a team battle. Right? They keep taking turns till somebody dies. So what we're going to do as an example in class is we're going to write a basic Pokemon battler where we have two people fighting each other to the unconsciousness. But it won't be as complicated as Pokemon because we just don't have the time to get into all that stuff. So over here, we'll get rid of everything that we had before. So the first thing that we have to figure out when we're doing this is what do we want to be building? So what's our goal to create? We want to be able to implement a fighting game, like a Pokemon battle, something like that, right? That's our overall goal. And so we might think, well, what is a Pokemon battle made up of? And two, what do we want to be able to do with a Pokemon battle? Yeah, it's a turn-based game, and it might be defined a little bit more, but we might just call this, like Pokemon battle to keep it themed. So now, yeah, that's fine. There's no main.cpp. That's cool. Didn't we add this to our snake list? Oh, it didn't delete anything here? Oh, this is not in the right directory. That's why. Okay. Great. So over here in the header file, again, we want to think about, well, what are we made up of? And what do we want to be able to do? So what is a Pokemon battle made up of? Right, it's made up of 2 Pokemon. How do we want to represent these 2 Pokemon? Do we want Pokemon 1 and Pokemon 2? Or do we want, a vector of Pokemon? Yeah, we could do that if we wanted to make it more extensible potentially in the future. Right, we'd have it as a vector, and then having Pokemon 1 and Pokemon 2 is not much more different than having the vector of it. But the vector makes things maybe a little bit easier to work with in the future. So we'll include vector. And we'll have an std : vector of Pokemon. And that type's not defined yet, but we'll worry about that later. I know we'll name it what my dad always used to call it, the Pokemans. Okay, so we have our Pokemon. What else is this game going to be made up of, right? This Pokemon battle. Well, that's if we wanted to have multiple Pokemon. So in general, like a Pokemon battle would be made up of trainers, and trainers have Pokemon. Then you might have like the 2 active Pokemon, right? But we're just going to assume there's 2 wild Pokemon fighting, right? Because we don't have time to do all that. Right? We might have like an integer to represent like what the current turn is. Or we might have something that's like, whose turn? What else would we have to have? But do those belong to the battle? No, those belong to the Pokemon, right? Right? But we have to think about like, well, what is the battle itself made up of? It's made up of Pokemon, I agree. And we might need to keep track of whose turn it is. What'd you say? Phases? Like, what are the phases? Oh, I don't know. But what we might like want to throw in here is like, well, what do we want to be able to do in a Pokemon battle? We want them to battle. Right? I mean, at the end of the day, that's what you want it to be able to accomplish. You want them to fight till unconsciousness. So we might just have a battle method here. And you might have other information getting things like, who is fighting. Or you might also have it where it does take 1 phase. But we might have just one thing, battle here. So we'll meet back up again on Friday. Think about what you want, like what the Pokemon are going to be made up of. Again, we're going to keep it simple, but you can see how our problem is made up of things, and we're going to want some interface into these objects.
There is a